Hello everyone, hello, greetings and salutations. Here I am at the seaside by the seagulls. And we're going to do some physics today. We're going to do a really hard topic today. So let's see who is here. Brave enough. Exploring Ginger, Grace, Greg, Katarina, and Shaka Cat. So, good for you for coming in here and learning something new, possibly. So today we're going to talk about torque. Torque is one of the most difficult topics in classical mechanics. So when you think about it, we go back to one of the most important equations in all of physics, F equals ma. So that's applying a force to something, and you can calculate what it will accelerate at based on that force applied. And we learned last week that this is really derived from the impulse momentum equation, where we said that force times a change in time is equal to a change in momentum, which is really mass times velocity final minus mass times velocity initial. This didn't look right, so I'm going to erase it. Where is my eraser? VO. Well, everything we've dealt with up to this point is not fixed at one point or at all. Well, it can be fixed, but it's not. If it was fixed in place, it wasn't showing any signs of movement at all. In this case, we're going to have one end of an object fixed. that can rotate about that point, like a lever arm or a wrench or something. So this here is a pivot point. So what happens if we apply a force to this end of the wrench or the pivot point? What's going to happen? Like you all know, just from life experience, what's going to happen? This thing is going to rotate, right? It's going to cause a rotation. So this force is going to cause a rotation. So if the force is trying to cause a rotation or does cause a rotation, we call it a torque. So a torque is a force applied at some distance from a pivot point. So we call this distance from the pivot point R. So from the pivot point to the force is R. And if you think about it, what would happen to this torque if the force was, let's say, let me erase this. Let's change the direction of it. Let's say we've got a force like that on it. From experience, what do you see happening to that bar rotating? Is it going to be easier to rotate that bar or more difficult to rotate that bar based on that angle the force is being applied at? And I'll wait for someone to answer that question. Easier, okay? So Grace says easier. Katarina says harder. Anyone else want to chime in? Want to agree with one or the other? Greg says more difficult. Yes, it is more difficult. You think about it, if you tried to, let's say you're going to open a door, push door, door opens when you push on it. Let's say you push at a real extreme angle like this, almost parallel to the door. Are you going to be able to open it? What if this force was like this on it? Would the door rotate at all? It wouldn't rotate at all, would it? And you notice that when you do open doors, you always want to, you instinctively push at what degree to the door? What angle do you open or do you push into the door? That's right, Greg. Instinctively, you push what angle into the door when you open it? 90 degrees. You push perpendicular. Typically you push perpendicular into the door. So if you have an angle of your force that is not perpendicular to the door, it gets harder and harder and harder to open it. So here's R, here is F. This angle is 90 degrees. So your torque is a maximum at 90 degrees between R and F. That's right, Shaka. So torque is maximum when R and F are perpendicular. So we have to be able to account for that in calculating torque. And the way we do that is we use this equation. Torque equals R cross F. R is a vector and force is a vector. Torque is a vector. So we have a vector that is the result of the cross product of R and F. That is not a multiplication sign. this here is called the cross product. It's a big X. And no one in math and science uses the multiplication sign like 3 times 6 equals 18. No one does that anymore. That's not to sound arrogant or rude or anything, but that's like middle school math. That's what you do in middle school. Even in high school in Algebra 1, you don't use X as a multiplication symbol anymore. If you want to say 3 times 16 in algebra and beyond, you do this, or you do this. So even this dot isn't used anymore. It's always multiplication with parentheses around the numbers, because we don't want to use up a symbol that can mean something else. So let's look at what R cross F means. Select all, delete. Hey Ben, what's up? All right, Ben, thank you for coming in. So torque equals R cross F. And we said that we needed to know, use a dot, we need to know the angle between R and F. So let's say here's the pivot point of something, here's R, here is the force, F. So we said that this would be the maximum torque. What the hell happened? This stupid ass thing. Whoa. Okay. So torque is maximum. So what trigonometric function is a maximum at 90 degrees? So we got to do sine of 90, cosine of 90. See which one is a maximum at 90 degrees. We know that's not tangent, because tangent of 90 is undefined. So you put in your calculator, cosine of 90 is 1, cosine of 90 is 0. So it's got to be the sine function. So R cross F really means take R, whatever it is, the absolute value of it, take F, the absolute value of that, and you multiply by the sine of the angle between R and F, and that's your torque. So that's how we calculate torque. And this T here is written as a tau. That's the Greek letter tau that we use to indicate torque. Very good, Greg. So, an important thing to here remember, you love the times tables? Yeah. Theta is the angle between R and F. So let's say that we had a situation where here we have a pivot point, here's R, and here is F. And the angle between them is 0. Well, R times F times the sine of 0 is 0. So that makes sense. If you're not pushing even into the door at any angle, it's not going to have any torque on it. So it works out nicely. There's another way to calculate the cross product of this, but it gets pretty involved, and I'm debating right now in my head whether we should do it or not. Let's do it. I think you can handle it. So that's the first way. Whoa, So we've got, here is R, and it's in the I hat direction. Remember I hat? I hat is a unit vector. Remember, this goes back to kinematics. And this is F, and we'll call this J hat. So we have this, remember this thing we did before? Let's see, R cross F, let's see, X, Y. Three-dimensional, we don't really need that. Okay, so what we can do now is say, here's the pivot point of some lever, a bar, and you're applying a force this way. We can say this is the torque, and we can put up here R, F, and then I hat, J hat, K hat, and then we repeat the first two, I hat, J hat. So let's just give these numbers to make it easier. This would be, let's make it 3 meters I hat, and we'll make this 10 newtons J hat. So what is R? It's 3 meters I hat. So 3, there is no J hat component to it. There is no K hat component to it. And we copy this over here, 3, 0. F is 0 I hat. There is no I hat component. There's 10 J hat, 0 K hat, 0, 10. So this is called a matrix. Matrix is a fancy way to calculate things. So what we do now is we do this. We diagonally multiply like this and add those values together. So we get 3 times 10 I hat plus 0 times 0 J hat plus 0 times 0 K hat. And then we subtract the values going the other way. Put big brackets there. Now we're going to go like this. 1, 2, 3. So 3 times 0 J hat plus 0 times 10 I hat plus 0 times 0 K hat. And we seal all that in with the final bracket. Something is wrong here. 3 times 10, 0, 0, okay. This gets messed up if you get sloppy with it. I might have messed this up. Yeah, I think I screwed this up. I'm gonna redo this. It's hard to write neat on this platform. Try this again. Okay. R, F, I, J, K, I, J. So this is 3, 0, 0. This is 3, 0. And then F was 0. 10, 0, 0, 10. 1, 2, 3. 1, 2, 3. What in the world is going on with this? This is 2 weeks in a row I've screwed up. It shows you I'm tired of school. I'm tired of this stuff. Something is seriously wrong. I'm gonna write it on paper first. Writing on this screen messes me up. Damn it. JKIJRF 30030 0 10 0 10. 1 2 3. That's it. My alignment was off. Alignment is way off. So odd how that messes me up writing on this screen. Okay. So I should go 0 0. This. Oh, can't write. So odd. Boom. 1, 2, up. Let me rewrite it. Part of the problem is I'm sitting sideways. I gotta sit like this. Okay. Let's try this again. I, J, let's write real neat. K, I, J, R, F. So it's 300 and then 30 0 10 0 0 10. I'm going to use this. I'm going to use shape. Okay, I'm going to go like this. Fucking thing. That makes sense. And I knew it was wrong before because you should not end up with any values in the I and J direction. That's just my crappy writing on this screen. That was the problem. Okay, so 0 times 0 times 0, 0, 0. So you have 0i, 0j, and you have 30k. We're just going to subtract the other direction. So we're going to do this. Oh. One, 2, 3. That's okay. So it'll be 3 times 0, which is 0, 0 times 10, which is 0, and 0 times 0, which is 0. So we're going to write that. 3 times 0, which is 0 j hat, plus 0 I hat, plus 0 k hat. So what's the only thing we get out of this? 30 k hat. So that means that our torque is 30 Newton meters in the k hat direction. All this tells us is that the torque is perpendicular to both I and J. So the torque is going to be into the screen. So this k hat just means into the screen. That really doesn't help much because it's so abstract. You just have to understand that torque is a vector and that the direction of the torque is always perpendicular to R and F. So it has to be k hat because I and J are already perpendicular, and the only other way something could be perpendicular to that would be another axis, k. And now you probably know why I told you this is a difficult subject. So any questions up to this point? rid of this now. Select all. Goodbye. Next thing is torque equals I alpha. Just like we have F equals ma, we have the exact same structure of equation, but torque now has to equal not m, I, and not a, but alpha. So you know what torque is. You should remember what alpha is, because this was what we covered with kinematics. It's angular acceleration. So if something is speeding up or slowing down as it's rotating, if it's speeding up in the rotation point, or in a rotation sense, or slowing down, think about a clothes dryer. When you press start, it starts off at rest and then it accelerates up to a maximum angular velocity. This I is something new. This is called the moment of inertia. This fucking tablet does not write nice. Moment of inertia. We can't just use m anymore, because we're not dealing with a point mass, we're dealing with an extended object. So you have to use this when dealing with extended objects. So use this when dealing with non-point masses, I should say. Like a long bar, a rod like this, or a hoop, a hula hoop, or a disc. That's not a very good drawing of a disc. A disc, something that's got some thickness to it, like a record. Those are just some of the shapes that I'm talking about. So each shape, we have to consider where is the mass concentrated in it. Well, in this, the mass is concentrated right in the middle, if it's uniform density. Here, the mass is concentrated in the outer edge of it. And here it's concentrated, we don't really know, it's pretty even throughout, right? There's no location. But if it rotates to the center, it tells us something. Now, what about if I had a big hammer, sledgehammer end on this? So this is the metal end of the sledgehammer, and this is just the wood. So if you think about it, if you held this end and tried to rotate this either way, it'd be easy, right? Wouldn't be a big deal. But what if you held the other end of the sledgehammer and tried to rotate it? Be much more difficult. That's because the distribution of the mass has changed. So that's why we have to use a moment of inertia, because it all depends on the shape of the object and where the mass is distributed in the object. So I'm going to erase this. Let's get rid of this and this, and let's look at a classic type of problem. Here's the fulcrum with pivot point. Here is a bar, like a seesaw. Now let's say that we have person or something on this side at this mass, and then someone over here sitting closer to the pivot point. We'll say that this is we'll say that this is 10 kilograms, and this is let's make it, we don't know. Let's say the distance from here to the center is 2 meters, and from here to here is 1 meter. What is the mass? What is the mass of this thing right here? We can calculate that. If it's at rest, there's no rotation. So no rotation at all. At rest. And no alpha. No angular acceleration. So we have to do some calculations. Greg says it's 20. He's done a quick calculation. Let's see if he's right. So we can say that the sum of the torques have to be equal 0. It means that the torque clockwise has to equal the sum of the torques counterclockwise. So what way is this force, of this weight of this object, going to try to rotate the seesaw? It's going to try to rotate it this way, which is clockwise, right? So this is a clockwise torque on the seesaw system. This one here is a counterclockwise torque. It's going to try to rotate it this way. This side's going to go down, this side's going to go up. That's counterclockwise. So remember, torque is Rf sine theta. So Rf sine theta for both sides. Well, let's do the clockwise side first. Clockwise side first. So R is what? It's 1. F is what? We don't know. It's mg. Sine of the angle between them is 90 degrees. So we do the same thing for the other side. Let's make this the right side. We'll do R for right side. And this is the left side. Left. So R of the left is 2. F is 10 times G. And the sine of 90 again. So now we can start canceling a bunch of crap out we don't need. You notice the G is on both sides, we can get rid of it. Sine of 90 on both sides, it's gone. So we end up with M equaling 2 times 10, which is correct, it's 20. Greg was right, 20 kilograms. Very good, Greg. Trying to think of another good problem. I think I've got one. Figures every week. Never fails. You think I'd catch on that I don't answer the phone around this time? Okay. We shape this ground here. Okay. Damn it. Oh, fuck. Who leaves messages anymore? Who freaking leaves voicemails? Oh, for God's sake. All right, this is a flag. And this here, let's say, is 5 kilograms flag. And this is a tension wire. We'll call this angle, we'll call it alpha. Let's make it 30 degrees. How about that? And there's a wind pushing into this way. Let's say the wind is pushing with 30 newtons of force. What is the tension in this cable? This is a cable. Cable tension. So what's the tension in that cable? Anyone want to try to figure this out? Well, we know there's no rotation, so the torques clockwise have to equal the torques counterclockwise. So which torque is clockwise, which is counterclockwise? Or are they both clockwise or both counterclockwise? Okay. One of each. Okay. So let's figure this out. Which way is the wind trying to make this system rotate? Well, we'll figure that this is the pivot point. So the wind's trying to make it do that, which is what? Counterclockwise, right? This, if the wind's pushing this way, it's going to put strain on this cable. So it's going to have a tension like that. That's not a tau, it's a T. So the tension is pulling this thing this way. So if we think about it, we pull this way and try to make the flagpole rotate to this way, this direction, which would be clockwise. So now we've got R. Let's say that this is 5 meters from here to here, and this is 15 meters from the bottom to the top. So you have R, F, sine of theta. So what is R? R is from the pivot point to where the force is applied, so that's 5 meters. F is what we're looking for, the tension, T, times the sine of the angle between them. Well, what is the angle between these? That's the tricky part with torque. You have to draw a perpendicular line. You have to draw a perpendicular line to this. This is a component of the tension we need, and we need this angle right here. Now, if you remember from algebra, or from geometry, parallel lines with the same interior angle, this is 30. So this is sine of 30. It's going to equal R, F, sine theta for the top. Now what's R for the top? It's 15. F is the 30 Newton wind force times the sine of 90. So now we can calculate this. Sine of 30, I think it's a half. Yep. So 5t times 0.5 equals 15 times 30 is 450 times the sine of 90, which is just 1. So it's 450. So this is 2.5t equals 450. So 450 divided by 2.5 is 180. So 180 newtons of tension have to be in that cable. which makes sense because it's such a high value, because it's pretty far from the application of the wind force. The wind force is 15 meters away from the pivot point, and the cable's attached pretty low. So that's why if you see towers, really tall towers with cables attached to them to hold them to the ground to prevent them from rotating, those cables are attached usually to the top. The lower you attach the cable on that pole, the more tension it's got to withstand. So that's a good application of torque right there. So engineers design the thickness of the cable, the angle of the cable with the ground, and how far it is up the pole based on a bunch of other factors, wind and whatnot. So we can do one more problem that doesn't involve static situation. These have both been static problems because nothing is rotating. There's no angular acceleration. So let's get rid of this. Select all. Goodbye. Boom. Okay, let's see here. I'm trying to think. Okay, got one. So here we have a ramp, inclined plane, and you have a disc. This is a disc that's rolling down the ramp. Okay, there has to be friction here, and friction has to be applied at the point of contact, allowing it to roll. So friction's acting this way. So let's figure out the friction. What is the friction force here? We'll say the mass of the disc is 10 kilograms. The radius is half a meter. What is the friction force? Actually, you know what? Let's make it a little bit more fun. Where's my freaking tools? Eraser. Let's figure out what mu is. What does mu have to be? Coefficient of friction. All right, so now we have, see ya, Greg. Sum of torques equals I alpha because there is an angular acceleration. So let's say that its angular acceleration is 0.5 meters per second, or sorry, radians per second squared. So what's the torque on it? Well, the friction force. The friction force is providing the torque. So RF sine theta. R is 0.5. F is the friction force, and the angle between them is 90. The I value of a disk, I just know it in my head. I use it at school all the time. It's 1/2 the mass of the disk times its radius squared. So 1/2 of m times r squared. Punjabi kitty, what's wrong? And then alpha we know is 0.5. So sine of 90 is 1. So it's 0.5 f equals 1/2 of the mass, which is 10. Radius is 0.5 squared times 0.5. So we have 0.5 to the third power times 10 times 0.5 is 0.625. Now we divide both sides by 0.5. We get 1.25. But that's not what this is. We want mu. That's not what we want. we want mu. So remember, friction equation is mu times normal. So what's the normal force? Well, remember we're on an incline. So the normal force is mg cosine theta equals 1.25. So let's give this, we'll give it to 30 degrees again. Let's make it 60. It works out nice. So mu times m times g times the cosine of 60 equals 1.25. So 10 times 9.8 times cosine of 60 is 49. So 1.25 divided by 49. We get 0.03. So mu is 0.03. And that's that. But now you know how to do both types. Static situations where there's no angular acceleration and where there's an angular acceleration. So that's it. Any questions about this? So while we're waiting for anyone to pop in with some questions, remember there's no Physikē premiere today at 3. Dea will be on at 3:30, and I will be on at 4. So my premiere is short. Pretty funny one though, I think. I like it. And then tonight we'll play that game with that Eskimo. Shaka Cat likes that owl man. I know this is like drinking water from a fire hose. It's impossible to fully understand this. How many different kinds of torques are there? There aren't, like forces, there's many types of forces, like applied force, friction force, normal force, tension force, spring force. With torque, it's just torque. It's just any force can be applied at any distance from any object's pivot point. So, what happened to all my subs? I don't know. What happened to the subs? Something happened to the subs? Let's check it. I have 83, which is about what I've had before. No, I think your topic's good, Katerina. That would be a good topic in the future, though. Maybe not this Hindi part, but I'd have to have more time on my hands to come up with questions about individual people. That might be a summer topic. That would be good for a summer topic, though. Good idea. Looks like my subs are okay, Shaka. You seeing something weird? You talking about this channel or the other channel? Oh, it's pretty good. It's about steady. My big subs, I'm at 563, which is up. Not many, but it's like one little tick up at a time. So, all right, everyone. Thanks for coming in and doing this. I know it's, like I said, drinking water from a fire hose. It's very difficult, but at least you're getting exposed to what physics is and all the math involved. Physics is math. It's all math pretty much, with understanding how things work just from experience. And like here's a perfect example of torque. Let's say you need to change your tire. You get a flat tire. Your wrench in your car, your what do you call it? What do they call that thing? Tire iron is pretty long. That's because you want a long lever arm between the bolt and where you apply the force. The longer the lever arm is, the easier it is to rotate it, because you don't have to apply as much force. I teach chemistry as well, Bruce. All right, everyone. Thank you all for coming in. Grace, Katerina, Shaka, anyone else here? Thanks for coming in, and we'll see you soon.
10,
Let's go for main engine start.
6, 5, 4, 3, 2, 1. And booster ignition, liftoff of Space Shuttle Discovery, taking the space station to full power for full science.
This is Mission Control Houston.
Discovery roll program. Roger roll, Discovery.
Discovery's roll maneuver is complete. It is now in a heads-down position on track for its flight to the International Space Station. Discovery flying 365 miles per hour, 1.5 miles in altitude, 7 miles downrange from the Kennedy Space Center. Discovery's engines are throttling down as the orbiter passes through the area of maximum pressure on the vehicle.